Okay, kiddos, we are back for not something that I can see. I have to turn this around so I can see what I'm doing. Okay, we're back for video number 3 on Module 9, Polyatomic Ions and Molecular Geometry. We've talked about what polyatomic ions are. Now we want to do molecular theory. It's the Vsepr theory. V-S-E-P-R. And what we have seen is that I think I want that to move more this way or bring it out. Yeah. This Vsepr, what we've done before with the Lewis structures, got a Lewis structure right here, which is the picture of a molecule of whatever in the world that is, CH2O. But molecules rarely occur in nature as two-dimensional flat structures, but they occur more as three-dimensional things. In other words, instead of just having length and width, they have a depth to them. They're 3D molecules. And what we have with our Lewis structures, it doesn't let us see what they look like, what they actually look like in real life. So this Vsepr theory lets us predict what the three-dimensional shape of a molecule actually looks for. And it sort of makes sense. This is an easy acronym to learn. This is valence. Because our Lewis structure is built based upon the number of valence electrons that each atom has. So this is valence. It's the outside, which is sort of like the shell, isn't it? So it's valence, shell. What are we talking about? We're talking about electrons. Valence, shell, electron, and now of course I forget what the P is. Pair. Repulsion. Now the only things in here that might not make sense right away is this pair repulsion. But when we're talking about all this stuff that we do with molecules has to do with valence electrons. It's the outside part, so it's the shell, and electrons. Now when you have your Lewis structures, electrons can have, atoms can have at most 8 electrons around them, and that's what they're looking for, with the exception of hydrogen, which tries to have 2 electrons in its outer energy level, just like helium does. They're all looking so that they have 8 electrons out in its outer energy level, and they occur in pairs. When it's full, you have 4 pairs of 2. So we have valence shell electron pair, that's where the pair comes from. Repulsion. What is repulsion? If something repulses you, you are not drawn towards it, but rather you are drawn away from it. You are repulsed by it. If you have 2 poles of a magnet, and one is positive and one is negative, what's going to happen when you push those magnets closer together? Are they going to go? Nope. They're going to go. They're repulsed by one another. So what this valence shell electron pair repulsion theory says is that the various different pairs of electrons in the Lewis structure don't want anything to do with each other. They all want to push each other just as far away as they can. It's like, you know, personal space. You've been friends with someone or come across someone who has a much smaller personal space than you do, and like they're getting right here in your face. You want to just back up, okay? That's what these electrons are doing. These electron pairs are doing. The pairs do not have a close personal space, but they back as far away from each other as they can. Now there's a point at which you can't back any further. There's a limit, but they have very big personal space. They go back as far as they possibly can. So this is what I have no idea how they pronounce that, Vsepr. If I looked on a DVD, on a CD that I have, it would probably tell me. Vsepr, I don't know, Vsepr, valence shell electron pair repulsion. And it's that valence shell electron pair repulsion theory that is what makes the three-dimensional shape of these molecules. Is what we have. Let's go ahead and start, instead of this one right here that's a little bit more complex, let's just take a very basic Lewis structure. Let's say that we have carbon tetrahydride. Carbon tetrahydride has a carbon in the center with a hydrogen at each end. Okay? These all want to push as far away as they possibly can from each other. Now, you know that that's a 90-degree angle, and you know that this is a 90-degree angle right here. This is 90 degrees, and this is 90 degrees. So if you just stay in a plane, the furthest that these bonds can push away from each other is 90 degrees. But it turns out that if you put a hook on this C here and pull it out, pull the carbon out a bit, then the electron pairs can actually be a little bit further apart from each other. And that is what happens. So I want you to look at your picture on page 290. This is picture right here. This is one that we're going to be looking at and talking about. And what we have is exactly what I have drawn here. This is the first picture right here. On the left, at the bottom of page 190, we have the Lewis structure for carbon tetrachloride. It's a 90-degree angle. Now, what they do is they draw in 2 dimensions what they would like you to be able to see in 3 dimensions. So we have carbon here in the middle, and that does not need to be near as long a line. Not sure where that came from. That's hydrogen. Now, if we had put our single covalent bond here, that would be about a 90 degree, but we're going to put our hydrogen here. And this angle is about 109 degrees, and it's going to be very important that you be able to draw these shapes and that you know your angles. Well, now we have 2 hydrogen atoms. Well, how are we going to draw the other ones? Well, we're going to have this dotted line here. And that means that this is sort of behind the plane. It's behind the surface. And then they draw these fat arrows somehow. And what this is supposed to be is the hydrogen molecule that is right out here in the front. These 2 are here and this is behind it. So you sort of have like a 3-dimensional picture. Now if you're like me, and I was texting Cindy back and forth last night saying, I can't do this, I cannot see things in 3 dimensions. I can sort of imagine what that looks like, but if I look at this picture here, photograph here that they have, it's 3-dimensional model of CH4's tetrahedral shape. This is tetrahedral. It's like a pyramid. There's your pyramid. Here's a C. You pull it up, and it's a tetrahedral. And that is not exactly right. A tetrahedral is a square where they pulled the cone out. Psst. Okay? And I said that, and I'm saying that that's wrong again. So what have I done? You have the 3 hydrogen here, your carbon atoms here sort of in the middle, and there is another hydrogen stuck out here that you can pull it up as a stick. Just go ahead and look at your picture, mull it over in your mind, go back and read your material a couple of times. My brain's much more stiff than yours is, So I'm hopeful that it will make more sense to you much more quickly. But what you need to know is that you have a carbon, you have these 4 hydrogen here. When the shape looks like that, you've got your tripod. Well, that's exactly what this is. This is my camera tripod. You have the 3 legs, and the stick that comes up at the top is the 4th leg. And this is called a tetrahedral shape. You must know tetra is 4, tetrahedral. The geometry of this molecule is tetrahedral. Okay, let's go ahead and move on. Okay, 291 Vsepr Theory states that the molecules will attain whatever shape is necessary to keep those electron pairs as far as is possible away from all of the other electron pairs. So when you have this particular configuration, which is you have 4 electron pairs around the center atom, that is when you're going to have a tetrahedral shape, 4 electron pairs. Okay? Moving right on. Now we've got another shape. This is the ammonia molecule. Ammonia is NH3. So we have N with a bond and a bond and a bond for the 3 hydrogen. This is ammonia, which is NH3. Ammonia. 1, 2, 3 bonds. So we have 2, 4, 6 electrons, 8 electrons, but this pair of electrons over here, this is not bonding. Okay, so this is what they call it's an S1. It's not an S, pyramidal. It's pyramidal. Now, I want to go back here. We still have 4 pairs of electrons around this center molecule, don't I? You know, we had the tetrahedral shape, which had 4 strong bonds around the central atom. 4 pairs of electrons around the central atom. We have 4 pairs of electrons around this central atom here, but the 3rd pair is non-binding. So this is what they call a pyramidal. Pyramidal. And it's not pyramidal, that's pyramidal. And you can see that pronunciation is actually given to you in your book. This is a pyramidal shape, that this particular configuration, particular arrangement of atoms in a molecule takes. What it is it's like the tetrahedral shape, except you take off that 4th stick. It's like my tripod without it going up, or without it being extended up quite so far. This is not as strong a... These 3 are trying to get away from each other, but not quite so much away from here. So what you see on page 292, we've got our Lewis structure, and I'm going to draw it differently. Nothing wrong with how I drew it. But if we draw it like this, we have NH, 1, H2, H3, here. This would be a Lewis structure. Then he rotates it just a little bit so that he can draw this in 3 dimensions. Probably it's very possible Matthew will be able to see this in 3 dimensions, and this is just so stereotyping. But in general, men are better able to see things in 3 dimensions than females are. However, it's totally possible that I'm wrong on this. So we have N with the non-binding electrons here. We have a hydrogen here. See how far it's gotten away? This is about 107 degrees between these next 2 hydrogen here. We have our slightly wider arrow. That means that this hydrogen is actually jumped out of the board. And then we have the hydrogen that is behind it. This angle right here is about 107 degrees, and this is a tetra. It is so not a tetrahedral. Tetrahedral is 4 bonding pairs of electrons. This is a pyramidal shape. 1 pair of the electrons are non-bonding. So pyramid shape, pulled up not quite as far as you have with the tetrahedral shape. Okay? Let's see. The next shape that he talks about is a bent shape, and this is the shape of a water molecule. Water molecule is H2O. Our central molecule is oxygen. H, H. Because when you think about it, what do you have as you're constructing it? You have an O that has 2, 3, 4, 5, 6. It has 6 electrons in its valence shell, and you have 2 hydrogens, and those hydrogens each have 1 electron. So we have 1 hydrogen, and we have a hydrogen now. Everybody's happy. Hydrogen has 2, oxygen has 8. We have 2 bonds between the hydrogens and the oxygen. We have a pair of non-binding electrons on 2 more sides of the oxygen. So let's see what this actually looks like when it's drawn in 3-dimensional form. You have a hydrogen here, and you have your oxygen, then you have your hydrogen again. Remember, Vsepr says that those electron bonds, pairs of electrons, are getting as far away from each other as they can. And this is 105 degrees. And if you look at the picture on page 293, this is really a 2-dimensional molecule, and it sort of looks bent, so we're being very creative here. And we say that this is the bent shape. Once again, though, the central atom, oxygen, has 4 pairs of electrons around it. 1, 2, 3, 4. 2 of those pairs, however, are non-binding. You know, they're not binding together with another molecule. I mean, with another atom. So, we have covered 3 different types of frameworks. And they're all based on a central atom. Central atom that has 4 electrons around it. If all 4 of those pairs of electrons connect to another atom, they're all bonds here, then this is called a tetrahedral shape. Have the same thing. You have, which one was it? I don't remember. Ammonium if you have once again, you have 4 pairs of electrons that are surrounding a central atom, but you only have 3 strong bonds here. This is the pyramidal shape. Pyramidal shape. And finally, you can have 4 pairs of electrons that are around a central atom, but only 2 of those pairs are actually bonds. This is what they call the bent shape. Right here, this is about 109 degrees. Right here, this is 107 degrees. Right here, this is 105 degrees. And this is specific information that you have to know for each one. Okay, that's our tetrahedron shape. Now, let's go ahead and take a break on this one. I'm going to go ahead and upload this video, and then I'll come back for one last teaching video, hopefully for this section of homework that's due